Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. And what we had seen in the previous module, we had seen the expression for the bit error rate of a multi-antenna wireless communication system, right. And we saw that for a system with L antennas, for the bit error rate of a multiple antenna wireless system with L antennas with L and this we had seen is given as the bit error rate. Let me simply write the expression down here, so as to remind you of that expression. It is 1 minus lambda by 2 to the power of L summation L equal to 0 to L minus 1, L plus L minus 1 choose L 1 plus lambda over 2 square. So, this is I am sorry 1 plus lambda over 2 raised to the power of L. This is our expression where we have said that lambda equals SNR divided by 2 plus square root of SNR divided by 2 plus SNR. This is our expression for the exact bit error rate of a multiple antenna wireless communication system with L antennas. It is L receive antennas and a single transmit antennas, that is receive diversity with maximal ratio combining, right. I hope everyone remembers that we considered maximal ratio combining as the optimal combining which maximizes the SNR at the receive, correct. Now, what we are going to do is we are going to develop an approximation for this to understand this better, to gain insights into the bit error rate performance of this wireless communication system. What we are going to do is we are going to develop a useful approximation for this bit error rate expression in a multi antenna system with L antennas. And therefore, what we wish to do is to develop an approximation for the bit error rate in a multiple right. So, we wish to develop an approximation for the bit error rate in a multiple antenna wireless communication system, and that approximation can proceed as follows. I am going to start with 1 minus lambda, the quantity 1 minus lambda by 2, which is equal to a half of 1 minus lambda, and this is equal to half. I am now going to substitute for lambda half 1 minus square root of SNR divided by 2 plus SNR, which is now equal to half. I can rewrite this as 1 minus square root of 1 over 1 plus 2 by SNR, that is dividing both the numerator and denominator inside the square root by SNR. I can write this as square root of 1 over 1 plus 2 by SNR, which is equal to half, again another equivalent way of writing this, half 1 minus 1 plus 2 over SNR to the power of minus half. And we can see that at high SNR, that is we have this approximation 1 plus x raised to the power of minus half approximately equal to 1 minus half x, where x is if or when x is approximately or x is very small or approximately close to 0, then I can expand 1 plus x raised to the power of minus half as approximately, I can approximate it as 1 minus half x. So, this expression here is approximately equal to half 1 minus half times twice over SNR, which can be now further simplified as half times, if you simplify this, I obtain 1 by SNR, which is equal to 1 over twice SNR. So, this quantity 1 minus lambda divided by 2 at high SNR, that is at high SNR, when SNR is high, therefore, 1 over SNR is small, I can approximate it as 1 over twice SNR. Now, let us look at the other quantity, that is 1 plus lambda by 2. Now, 1 plus lambda by 2 equals half times 1 plus square root of SNR divided by 2 plus SNR, which again is, I can write this as half times 1 plus square root of 1 over 1 plus 2 over SNR, which is equal to half, another equivalent way of writing this, half 1 plus 2 over SNR raised to the power of minus half, which I can now approximate as half times 1 plus 1 minus half at high SNR, when 1 by SNR is a small quantity, 1 minus half twice over SNR. And now, this I can further approximate this as equal to half of, if I simplify this, half of 2 minus 1 over SNR. Now, 1 over SNR at high SNR, 1 over SNR is approximately equal to 0. So, we have 1 over SNR approximately equal to 0 at high SNR, implies this quantity 2 half times 2 minus 1 over SNR is approximately equal to 2. Therefore, this is approximately equal to half times 2, which is equal to 1. So, we have shown that at high SNR 1 plus lambda divided by 2 can be approximated as 1, right, at high SNR, that is when 1 over SNR is close to 0, 1 plus lambda by 2 can be approximated as 1. Therefore, we have the following approximations. We have, therefore, at high SNR, we have the following approximations. We have 1 minus lambda by 2 approximately equal to 1 over twice SNR, and 1 plus lambda by 2 is approximately equal to 1. And now, I can substitute this in my expression for the bit error rate, the average bit error rate. I have the average bit error rate equals 1 minus lambda by 2 raised to the power of L summation L equal to 0 to L minus 1, L plus L minus 1, choose L, 1 plus lambda over 2 raised to the power of small l. But we have seen previously that 1 minus lambda by 2 can be approximated as 1 over 2 SNR at high SNR. So, therefore, at high SNR this is approximately equal to 1 over 2 SNR raised to the power of L summation L equal to 0 to L minus 1, L plus L minus 1 choose L times, and we have also seen that at high SNR 1 plus lambda by 2 can be approximated as 1. So, therefore, this is 1 to the power of L, which is basically 1. So, this is approximately equal to at high SNR. This approximation, mind you, is valid at high SNR. This is equal to 1 over twice SNR raised to the power of L into summation L equal to 0 to L minus 1, L plus L minus 1 choose L, and summation L plus L minus 1 choose L from L equal to 0 to capital L minus 1. This can be shown to be 2L minus 1 choose L, and therefore, this is equal to 2L. Finally, we obtain the high SNR approximation as 2L minus 1 choose L 1 over 2 SNR raised to the power of L. So, therefore, what we have obtained is we have obtained a high SNR approximation for the bit error rate of the wireless communication system with L antennas, and we have shown that this is 2L minus 1 choose L times 1 over twice SNR raised to the power of L, and therefore, at high SNR the bit error rate of wireless communication system with L antennas can be approximated as the approximate bit error rate equals 2L minus 1 choose L times 1 over 2 SNR raised to the power of L. This is the expression for the approximate bit error rate at high SNR. Now, let us simplify this considering again L equal to 2 antennas. For L equal to 2, this is for the case with L equal to 2. For L equal to 2, we have approximate bit error rate equals 2L minus 1 choose L times 1 over 2 SNR raised to the power of L, but L is equal to 2. So, 2L minus 1 is 3 choose 2 1 over twice SNR raised to the power of 2, and 3 choose 2 equals 3 times 1 over 2 square 4 times 1 over SNR square, which is equal to basically 3 over 4 times 1 over SNR square. So, for L is equal to 2, for L is equal to 2, the average, the approximate average bit error rate at high SNR is given as 3 by 4 times 1 over SNR square. So, this, what is this? 3 by 4 times 1 over SNR square, this is approximate bit error rate for L equal to 2 antenna system, for a system with L equal to 2 antennas at high SNR. So, this is basically the approximate bit error rate for a system with L equal to 2 antennas at high SNR. So, what we have shown in this module is basically in this module we have started with the exact bit error rate expression for a wireless communication, multi antenna wireless communication system, and then we derived a suitable approximation for this multiple antenna system at high SNR. At high SNR means we use the condition where SNR is very high. So, 1 over SNR is very low, that is approximately close to 0. Under this scenario, the approximate bit error rate can be derived as 2L minus 1 choose L times 1 over twice SNR raised to the power of L. That is the expression for the bit error rate at high SNR in this multiple antenna wireless communication system. And we are going to use this result and perform further simplifications in the subsequent modules. Thank you very much.